Hi everyone, so today we're going to continue with our chapter 7 entitled Acid-Base Titration. So here is the description for this chapter. The expected outcome is to understand and state the principle of titration, define and identify Arrhenius and Bronsted-Lowry acids and bases. Next, define and identify the conjugate of a given acid or base. And the last one, describe and apply the titration curves, calculation, and indicator to solve the problem regarding acid-base titration. Here is the content for this topic. So we will include all the theories of acid-base titration and also the auto-pyrolysis of solvents. In this case, we focus on the water, the molecule of water. Next is the acidity of solution, then the method or the how we can do for the acid-base titration. Next is endpoint detection from the graph, and the last one is the indicators for a titration. So here is the application of acid-base titration. So basically, we will have a standard solution, either acid or base, and then this standard solution is basically we will use as a titrant that contained in the burette. Okay, and after we do the titration, and we will see the result in the graph. So basically the application for acid-base titration is in the elemental analysis, the determination of inorganic substance, determination of organic functional groups, and also determination of salts. So here is the theories of acid-base titration. So the first theory comes from the Arrhenius theory. Arrhenius is the scientist that won a Nobel Prize in 1894. He said that acid is any species that can produce hydroxonium ions. Hydroxonium ions is H3O plus. Okay, so this is actually comes from the H plus mixed with water molecule. And the base is a species that produce hydroxyl ions in aqueous solution. Okay, hydroxyl is OH minus. So if any of species that does not include acid or base, so he estimate that it cannot produce H plus and OH minus ions. Another theory comes from Bronsted-Lowry. He said that acid is the proton donor. Proton here is we refer to the H plus, okay, and base as the proton acceptor. So in this case, we have another terms, a new terms that we call as amphoteric substance. Amphoteric is actually we refer to the it can function as a acid or base. Okay, so it means that it has a potential to become acid and it has potential to become base. Okay. And next is we have also another one theory comes from Lewis. Okay, so this scientist said that the acid is accept a pair of electrons, whereas for base it donate a pair of electrons. Okay, so basically Lewis theory is actually focusing on the chemicals acid base that doesn't have any H plus or OH minus. So Lewis theory comes when some chemicals that doesn't have any H plus and OH minus but shows the acid base properties. Okay, so this is that's why we need to know about the Lewis theory too. So here is the strong electrolyte, strong acid, weak acid, and also strong base and weak base list. Okay, so you can refer here. There are a variety of kinds. Okay, you can see from the list. And what I want to mention in here is that the strong electrolyte, it is completely dissociated. Okay, when we talk about the acid, when we talk about base, both must be dissolved in water. It means that even though it is a powder, okay, the acid will have a reaction to show the properties of acid, let's say, when it react with water, okay, because water, it has a potential to undergo autopyrolysis. Okay, this autopyrolysis is the properties, the unique properties of a water, that it can shows the the properties of certain chemicals, like for acid or base. Okay, so another term is weak electrolyte is partially dissociated, and after that I will show you how we can determine the pH value for the strong acid or weak acid and strong base, weak base. Okay, so here is the list. So please just take note all the chemical list here. Okay. So now we go for the autopyrolysis of solvents. Okay, what is the meaning of autopyrolysis? It is a self-ionization. Okay, as you all know that water is a neutral, and basically it has a pH of 7. Okay, so basically when we have a autopyrolysis of solvents, okay, like in this case is water, okay, because we know that water is the universal solvents. Okay, so in this case, we use a molecule of water, and then it will dissociate to become H3O plus and OH minus. Okay, so in this case, we can estimate that the equilibrium constant value for water is 1 times 10 to the power of minus 14. Okay, so in this case, we can estimate and we can write the full equilibrium expression. Okay, so as you know that water, okay, water is the pure liquid, so we can negligible the concentration of water, hence Kw equals to H plus times with OH minus. Okay, so another terms that commonly used in analytical chemistry is a protic solvent. Okay, what is protic solvent? A solvent that involves the transfer of H plus from one molecule to another can undergo self-ionization. Okay, so protic solvent, it does contain with H plus, and it can transfer the H plus. Okay, for instance, a water, a methanol, or ethanol. Okay, any molecule that have a H plus, okay, it has a potential to transfer the H plus. Okay, when we talk about the polyprotic, poly means many, more than one. Okay, so here we can see that we know that there are certain acids and base that might contain with more than one H plus or proton. Okay, so here, for example, the phosphoric acid, okay, you can see the H3PO4 is the phosphoric acid. It will dissociate, okay, it will dissociate when it mixes with water to become H2PO4 minus, okay, in a acidic medium. Okay, so this is the, you can see that Ka1 is referred to the equilibrium constant value for acid dissociation first step. Okay, for the first acid dissociation, so that is the value 7.11 times 10 to the power of minus 3. And then the second step is H2PO4 minus mixed with water to produce HPO4 2 minus, okay, in an acidic medium. So this is the second acid dissociation. So the value will be a bit different, not similar. Okay, so it depends on the strength of the hydrogen the protons, okay, to either it is easier to dissociate or it's difficult to dissociate. It depends, okay. So like for the HPO4 2 minus mixed with water, then it will produce the phosphate ion in a medium, in an acidic medium. Thus it will have a very small acid dissociation value, about 7.1 times 10 to the power of minus 13. Okay, so in this case we can see that polyprotein, it does have acid dissociation value more than one, okay, because it does contain with more than one proton, okay. So next is aprotate solvent. When we talk about aprotate, it means that the solvent does not have any acidic proton. So what they have is that only the transfer of electron might contribute to these acid base properties, okay. So for instance, like acetonitrile, okay, CH3CN, okay, and all anything that can show the acid base properties. For an aqueous solution of 0.1 molar HCl, HCl is the hydrochloric acid, and as you know that hydrochloric acid is a strong acid, and when we have a strong acid like hydrochloric acid dissociate, it will become proton plus chloride ion. So here, as you know that the strong acid and strong base will completely dissociated. So what we can see here is that the concentration of the proton will be equals to the concentration of HCl, the hydrochloric acid. So here what we can see that due to the completely dissociated, so we can simply use the formula of pH equals to negative log H plus, and we can easily get the value of the pH, okay. So another important point that you need to consider is the multiply of H plus with OH ion um, must be equals to 1 times to 10 to the power of minus 14, okay. This is related to the formula that comes from the pH plus POH equals to 14. That's why in the scale of acid base meter, okay, you can see, you can take note that the range is only from 0 until 14. Okay, so here we go for the next subtopic is the about the ionization of strong acid and bases. Okay, so here we can estimate that the strong acid and strong base will 100% ionization. It means that the strong acid and strong base will completely react or completely dissociate. Okay, dissociated. Okay, so here we can see, consider the concentration of 2 times 10 to the power of minus 3 molar of hydrochloric acid. Thus, the H plus is equals to the concentration of the hydrochloric acid. Thus, you can see the pH is equals to 2.7. And you can see that the pH is lower and it is in under range of acid. So here is the example of calculation. Okay, so what is the pH of solution containing 0.1 molar of sodium hydroxide? First of all, you need to know what is the solvent. So like for this example, you can see the sodium hydroxide is a kind of a strong base. Okay, so when we talk about strong base, first of all, it's better if you can write the acid dissociate. I mean the base dissociation chemical reaction, and after that you can identify either there is a H plus or OH minus, okay. So it is much easier to identify. So here the final concentration, okay, you can see that the sodium ion is equals to the hydroxyl ion, so it equals to 0.1 molar. So due to this value, and as you can see that sodium hydroxide is the strong base, so it will completely dissociated. When it is completely dissociated, so you can simply use the formula of POH equals to negative log OH minus. Okay, so from here you can see that the POH value will give you negative log 0.1 equals to 1. So the question asked is the pH value, not a POH. So you must be careful to answer the question. Okay, so now the pH must be 14 minus 1. So the pH should be 13. And when we talk about the higher value of pH like 13 is under a basic region. Now let's look for the weak acid. So the first step before we can calculate the concentration of weak acid is you need to know how to write the full chemical reaction involved. Like for this Ha will dissociate become proton and the conjugate base. Okay, so in this case uh, weak acid, it must have a pair. Okay, acid base pair. Consider the weak acid, Ha conjugate acid, and A minus is the conjugate base. Okay, so these both are the acid base pair. So by the time you want to write the equilibrium constant, so you must look at the Ka there, because Ka is actually referred to the acid dissociation value. Okay, that comes from the equilibrium constant. Okay, for this process acid dissociation. Okay, for example, a solution of acid, weak acid, okay, 0.03 molar was found to have the concentration of proton about 6.5 times 10 to the power of minus 4 molar. Calculate the Ka or the acid dissociation value for the acid. So first of all, you need to write the chemical reaction, the dissociation chemical reaction, and then you write the equilibrium constant expression. Okay, and after that you can identify the concentration, like what you can get from the question. The concentration of a proton must be equals to the conjugate base. Okay, equals to 6.5 times 10 to the power of minus 4 molar. So here you can see that the concentration is equals to 0.03 minus 6.5 times 10 to the power of minus 4. Okay, so after that we can get 2.9 times 10 to the power of minus 2 molar. So here you can simply just write the the value into the equilibrium constant that you write just now. Okay, you can write the value in the expression. Okay, so finally you will get the Ka value equals to 1.5 times 10 to the power of minus 5. And by the way, before that, equilibrium constant or acid dissociation constant or base dissociation constant, there is no unit for that. Okay, so just ignore the unit for the equilibrium constant. So now we consider for the weak base. Okay, for every weak acid there is always an associated weak base. Yes. Okay, so here we can see that the anion A act as a weak base. In this case we can see A minus is a conjugate base. Okay, when it mixes with acid or weak acid, it will form another weak acid. Okay, but H2O is just we can consider it as a weak acid. Okay, and when it produces the Ha plus with hydroxyl ion, so in this case the hydroxyl ion is the conjugate base. Okay, so the way you write the Kb value must be equals to the one that you learn in the previous slide. Okay, the same concept. Okay, so when we have this weak acid and base to ionize, so how we can determine the equilibrium mole or equilibrium amount of the reaction? Okay, so the first step is you need to identify the chemical reaction. Okay, second one is you simply write the initial value of the weak acid and also the proton and the A minus. And after that, you write the equilibrium. Okay, when it reach equilibrium, you must understand that there is a slightly changes in concentration. Okay, so um, we need to put here like C naught minus C1. Okay, C naught minus C1, and then it will give the concentration H plus C1. Okay, and A minus also C1. Okay, so in this case, Ka is the acidity constant. So you need to know that we still use this K value. Okay, for to solve this problem. Okay, in this stage, you must do assumption. Okay, what is the assumption? First one is contribution of H plus from water is negligible. Okay, because as you know, water is a pure liquid and we can ignore the value of concentration of water. Second one is you need to know also that the Ka, the acidity constant, is much less than 1. So what we can estimate that C1 is much smaller than C naught. Okay, so what we can do is that the C naught minus C1 is similar to C naught. Okay, so we can estimate that C1 is very very small. That's why it's still a C naught. Okay, so next is Ka will be equals to C1 to the power of 2 and divide C naught. Okay, so at the end you will get that H plus is equals to square root Ka times with C naught. Okay, so you can do this method or any method that you can easily to understand. Okay, so this is another method. Okay, what about for the weak base? Okay, for the weak base, you must follow the same concept, the same procedure. Okay, you must write first the chemical reaction, and after that, you need to have your initial, and you need to have the C naught. Okay, for the base, and it will dissociate become the BH plus and OH minus. So both are 0 at initial. Then after that, when it reach equilibrium, the B will become C naught minus C1, and the BH plus will become C1. OH minus will become C1. So after that, you need to write the mathematical equation. Okay, the Kb equals to what? Okay, so in here, the assumption is still similar. The first assumption is contribution of OH minus from water is negligible, and the second one is you need to follow that Kb is less than 1, is much less than 1, and the C1 is much less than C naught. Okay, that's why when C naught minus C1, we can simply ignore the C1. Okay, and after that, you can simply calculate the concentration of OH minus. Okay, so this is the same concept, just like what I explained just now. So we can skip to the next. So here is the what we call as the titration curve. Okay, the titration curve of weak acid. Okay, so here we can see that um, y-axis is the pH and the x-axis is the burette volume in milliliter unit. So what you can see here is that, okay, so we can simply use, okay, pH equals to pKa plus log A minus divide HA. Okay, so here you can see that this formula is a very famous to be used for the weak acid. Okay. Okay, what about for neutral ions? Okay, so in any case, neutral ions are not affected by pH, and it does not react with water to form H plus or H minus. So neutral ions are only from strong acid or strong base. Okay, it is not many. Okay, so here is the example of the neutral ions. Okay. So basically, when an ion and plus with a cation, it will form a salt. Okay, so this is what we call as a neutralization titration. So let's say this is the titration curve. Okay, that can you identify what is in the conical flask and what is in the burette? So in this case, you can see that when the volume of acid added is 0, the pH is at 14. It means that in the conical flask is base. Okay, so in the conical flask is base, whereas in the burette is the acid. Okay, so here we can see that when strong acid react with strong base, okay, by using two different kinds of indicators, we can see methyl orange and phenolphthalein. Okay, but during our lab session we use phenolphthalein, right? Okay, so here we can see a very sharp peak. Okay, very sharp uh, sliding down. Okay, that shows the equivalent points occurred in this range. Okay, so as you can see that when the curve is starting to when the lines start to curve, it shows starting point of end point. Okay, and in between the end point there is a one point we call as equivalent point. Okay, at this equivalent point it shows that it is completely dissociated. Okay, so basically the equivalent point is at pH 7 if it's a strong acid. And now let's go for the strong acid versus a weak base. Okay, so by the time we want to do a titration for acid base, for the strong acid and weak base, so basically the equivalent point will go to um, more to the lower pH value, which means that it will be less than 7. Okay, the equivalent point. So in this case we can see that the mixture in the mixture strong acid is dominant. Okay, so that's why the equivalent point is less than 7. Okay, what about weak acid plus weak acid react with strong base? So here you can see that the equivalent point will become much higher than 7. Okay, this is due to the strong base dominant in the mixture. Okay, so that's why it will give you equivalent point larger than 7. So now for the weak acid mixed with a weak base, we can see that not very clear equivalent point, and it is not easy to identify. Okay, when we do a titration with weak acid and weak base. Okay, now like for the standard solutions, we have a strong base, strong acid and strong base, and basically the property is it is completely react with the analyte, and it also have a sharp endpoints. And for this strong acid and strong base, we advise never use weak acid and bases as standard reagents. Okay, because it will makes the reaction incomplete. Okay, for the standard solution of acids, like for example, a dilution of concentrated sulfuric acid, hydrochloric acid, or perchloric acid. Okay. Another example for solution of bases like sodium or potassium, barium hydroxides. Okay, so this is one kind of strong base. Okay, so here is the titration of strong acids and strong base. So you can see. Okay, so this is how they identify. Okay, so you can see the phenolphthalein transition range. Phenolphthalein is the indicator. So it will show the color changes in that range only. Okay, so you need to choose wisely what is your indicator. Okay, for different I mean for a different like solution, you need to choose your indicator. Otherwise, it will not give you any changes. Okay, so you cannot identify the endpoint. Okay, so from here you can see. Okay, when you increase the concentration, okay, when you increase the concentration of the titrant, okay, it will give you a sharp, okay, a sharp endpoint. So here you can see that as the concentration of a titrant decrease, the endpoint break decrease. Okay, so the selection of indicator becomes more critical. So here indicator play a main roles. Okay, so it's very important for you to choose wisely your indicator. Okay. Next, this is the also the titration. Okay, the mirror image of hydrochloric acid. Okay, hydrochloric acid titration curve. Okay, by using different kinds of indicator like phenolphthalein and bromothymol blue. We have a lots of indicators. Okay, so I will show you after this. Okay, for the strong acid and strong base titration, okay, the process are actually uh, can give a very clear of endpoint. Okay, so what is actually happen during the titration is that when the pH is approaching the equivalent points, the concentration of H plus concentration gets very small. Hence, with a small addition of base, it will give a big impact, big differences in the pH value. Okay, so when it's near the equivalent point, the big changes in pH is observed. Okay, so we can see that basically for the strong acid and strong base titration, phenolphthalein transition, phenolphthalein will be used as an indicator. So basically, the equivalent point is at pH 7. Now, for this titration curves of weak acid with a strong base, okay. So here you can see that when there's a weak acid with and strong base in the titration, okay, it shows that it will at the equilibrium point it will slightly basic. Okay, just like what I mentioned in the previous slide. Okay, due to the salt contain the conjugate base. Okay, which is able to recombine with a proton. Okay, that's why you can see that just like what I said just now that the base is dominant in the mixture due to the conjugate base. Okay, so basically you can see that there's a certain area we call as a buffer area. So this is a buffer region. So we can see this is a buffer region. Okay, this is buffer region. Okay, now I will show you on how to find the equivalence point in the titration curve. As you all know that after you do the experiment of acid-base titration, you need to prepare or construct a graph, okay, of pH versus burette, titrant volume, okay. So basically, it will show you something like this figure, okay. So here you can see this is the kind of graph, okay. So here is the buffer region, okay. So this is just a buffer region, okay. And this is what we call as already reached the plateau of a reaction, okay. So here you can see that at this point, at this region, this is where the equivalent points are located, okay. So first step is you need to use a ruler and you need to draw the lines follow the flat, more horizontal part of the curve, okay. So just draw a straight line, okay. Just draw a straight line between these two lines. Okay, next draw a line that follow the flat, more vertical part of the curve, okay. So this is just uh, the vertical line that you, okay. And the third step is just take note the point that the line merge, okay, the line merge, okay. So we can figure out that these two spot, okay, is the intersection, okay, the intersection. This is the top intersection. This is the top intersection, whereas this is the bottom intersection. So the equivalent point will be in the middle. So next, when you see the line, okay, that from the two intersection that cross with the line that we found here, so that is your equivalent point. So the fifth step is to draw a vertical line from the equivalent point to the x-axis. Okay, from the x-axis to the point to the equivalent point. So next, where the line crosses the x-axis is the volume at the equivalent point. So here we can estimate that at 28.7 milliliter in this case. Okay. Okay, now we going to choose the best indicator for titration. Okay, so what are the criteria and what you should know in order to choose the indicators? Okay, uh, it is better if we can choose an indicator that can show a very clear changes. Okay, the color changes are very clear. Okay, so that we can estimate very clear the endpoint. Okay. So this is the list of the acid-base indicators. As you can see that we have thymo blue, methyl yellow, methyl orange, bromocreso green, methyl red, and so on. But the differences between these different kinds of indicators is the transition range. Okay, so basically when we want to uh, consider strong acid and strong base. So we will estimate that the pH equivalent point is at pH 7. So we will use the indicators that have a transition range in between. Okay, I mean the value like pH 7 in between range of the indicators. Okay, so that is how we can choose the best indicator, okay, for our experiment. So here we can see a very clear also, okay, the color changes, okay. So basically when we use like for example phenolphthalein, okay, when we use the phenolphthalein like from the acid, okay, let's say your sample is acid, okay, and your in the burette is base, okay. So from the acid range it will become colorless, okay. So by the time the H plus is gone, it will become the red violet, the very light pink, okay. So this is a very or a very common indicator we use for the strong acid and strong base titration, okay. Other than that, we also can use but we need to be careful with the transition range of the pH. In chemistry part, okay, acid base indicators actually shows, like for this example is a phenolphthalein, okay. When it was in a acidic solution, the compound of phenolphthalein will give you colorless solution, okay. So by the time when the H plus is gone and only water is left, okay, so it will turn to become a light pink, okay, or in this case a red, okay, but it is a more to the light pink color, okay. So this is what you must understand how the indicators work. So this is the chemical reaction that happen for the indicators, okay. Just like for the acid type indicators, H here is actually H here is refer to the proton, and this IN is indicator, okay. When it mix with water, it will become indicator minus plus with H3O plus, okay. This is a base color, okay. And in this base type indicator, the indicator, okay, will plus with H2O and it will form the acid color, okay. The indicator will accept H plus, okay. Okay, so from this summary, we can see that the color changes is occurred when the H plus, the proton, is gone or added, okay. So this is what we try to figure out when we do titration, okay. Okay, so that's all from me, guys, and that's all for chapter 7, and thank you for watching. Bye.